As we all learn early in school, the Earth's shape is very close to a sphere. Pictures taken from space by astronauts and by orbiting satellites also show us that the Earth is a ball rotating in space. Today it seems almost nonsensical that many of our ancestors thought the world was flat. But to ancient sailors voyaging across the Mediterranean Sea, the shape and breadth of the Earth's oceans and lands were hidden. Imagine standing on one of their ships, looking out at the vast ocean, with no land in sight. The surface of the sea would seem perfectly flat, stretching out and meeting the sky along a circular horizon. Given this view, perhaps it is not so surprising that early sailors, believing the Earth was a flat disk, feared their ships would fall off its edge if they ventured too far from land. We also gain information about the shape of the Earth when we watch the sun set when there are clouds in the sky. The clouds continue to receive the direct light of the sun, although it has already set, as seen at ground level. The movement of solar illumination across the clouds is easily explained by a rotating sphere called Earth. Actually, the Earth is not perfectly spherical. The Earth's equatorial diameter, at about 12,756 kilometers (7,926 miles), is very slightly larger than the polar diameter, which is about 12,714 kilometers (7,900 miles). As the Earth spins, the outward force of rotation causes it to bulge slightly at the equator and flatten at the poles. The difference is very small, about 0.3%, but strictly speaking the Earth's squashed shape is closer to what is known as an oblate ellipsoid, not a sphere. An even more accurate representation of the Earth's shape is the geoid, which is a reference surface based on the pull of gravity over the globe. It is defined by a set of mathematical equations and has many applications in mapmaking, as well as navigation. The Earth spins slowly on its axis, an imaginary straight line through its center and poles, a motion we refer to as rotation. We define a solar day by one complete rotation, and for centuries have chosen to divide the solar day into exactly 24 hours. The north and south poles are defined as the 2 points on the Earth's surface where the axis of rotation emerges. The Earth's rotation is important for 3 reasons. First, the axis of rotation serves as a reference in setting up the geographic grid of latitude and longitude. Second, it provides the day as a convenient measure of the passage of time, with the day in turn divided into hours, minutes, and seconds. Third, it has important effects on the physical and life processes on Earth. All forms of life on the planet's surface are governed by the daily rhythms of the sun. Green plants receive and store solar energy during the day and consume some of it at night. Among animals, some are active during the day, others at night. The day-night cycle also sets in motion the daily air temperature cycle that is observed in most places on the Earth. The directions of large motions of the atmosphere and oceans are also affected, as the turning of the planet makes their paths curve. Weather systems and ocean currents respond to this phenomenon, which is known as the Coriolis effect. Finally, the Earth's rotation, combined with the Moon's gravitational pull on the planet, causes the rhythmic rise and fall of the ocean surface, which we know as the tides. It is impossible to lay a flat sheet of paper over a sphere without creasing, folding, or cutting it, as you know if you have tried to gift wrap a ball. This simple fact has caused mapmakers problems for centuries. Because the Earth's surface is curved, we cannot divide it into a rectangular grid any more than we could smoothly wrap a globe in a sheet of graph paper. Instead, we divide the Earth into what is known as the geographic grid. This is made up of a system of imaginary circles, called parallels and meridians. Imagine cutting the globe just as you might slice an onion to make onion rings. Lay the globe on its side, so that the axis joining the north and south poles runs perpendicular to your imaginary knife and begin to slice. Each cut creates a circular outline that passes around the surface of the globe. This circle is known as a parallel of latitude, or a parallel. The Earth's longest parallel of latitude is the equator, which lies midway between the 2 poles. We use the equator as a fundamental reference line for measuring position. Now imagine slicing the Earth through the axis of rotation instead of across it, just as you would cut up a lemon to produce wedges. The outlines of the cuts form circles on the globe, each of which passes through both poles. Half of this circular outline, connecting one pole to the other, is known as a meridian of longitude, or, more simply, a meridian. Meridians and parallels define geographic directions. When you walk directly north or south, you follow a meridian. When you walk east or west, you follow a parallel. There are an infinite number of parallels and meridians that can be drawn on the Earth's surface, just as there are an infinite number of positions on the globe. Every point on the Earth is associated with a unique combination of one parallel and one meridian. The position of the point is defined by their intersection. Meridians and parallels are made up of two types of circles, great and small. A great circle is created when a plane passing through the center of the Earth intersects the Earth's surface. It bisects the globe into two equal halves. A small circle is created when a plane passing through the Earth, but not through the Earth's center, intersects the Earth's surface. Meridians are actually halves of great circles, while all parallels except the equator are small circles. Because great circles can be aligned in any direction on the globe, we can always find a great circle that passes through 2 points on the globe. We label parallels and meridians by their latitude and longitude. The equator divides the globe into 2 equal portions, the northern hemisphere and the southern hemisphere. Parallels are identified by their angular distance from the equator, which ranges from 0 degrees to 90 degrees. All parallels in the northern hemisphere are described by a north latitude, N, and all parallels south of the equator are given as a south latitude, S. Meridians are identified by longitude, which is an angular measure of how far eastward or westward the meridian is from a reference meridian, called the prime meridian. The prime meridian is sometimes known as the Greenwich meridian because it passes through the Old Royal Observatory at Greenwich, near London, England. It has a longitude value of 0 degrees. The longitude of a meridian on the globe is measured eastward or westward from the prime meridian, depending on which direction gives the smaller angle. Longitude then ranges from 0 degrees to 180 degrees, east or west, E or W. Used together, latitude and longitude pinpoint locations on the geographic grid. Fractions of latitude or longitude angles are described using minutes and seconds. A minute is 1/60th of a degree, and a second is 1/60th of a minute, or 1/3600th of a degree. So, the latitude 41 degrees, 27 minutes, 9, and 41 seconds, 0, north. Lat. 41 degree 279 410 N means 41 degrees north plus 27/60ths of a degree plus 41 3600th of a degree. This cumbersome system term has now largely been replaced by decimal notation. In this example, the latitude 41 degrees 279 410 N translates to 41.4614 degrees north. Degrees of latitude and longitude can also be used as distance measures. A degree of latitude, which may a short distance in a north-south direction, is equal to about 111 kilometers 69 miles. The distance associated with a degree of longitude, however, will be progressively reduced with latitude because meridians converge toward the poles. For example, at 60 degrees latitude, a degree of longitude has a length exactly half of that at the equator, or 55.5 kilometers 34.5 miles. A third axis exists for defining locations. Elevation, that is, height or altitude, complements latitude and longitude. Elevation is usually measured from sea level, but can also be expressed as a distance from the Earth's center. The problem of how to best display the Earth's surface has puzzled cartographers, or map makers, throughout history. The oldest maps were limited by a lack of knowledge of the world, rather than by difficulties caused by the Earth's curvature. They tended to represent political or religious views rather than geographic reality. Ancient Greek maps from the 6th century BC show the world as an island, with Greece at its center, while medieval maps from the 14th century place Jerusalem at the locus. But by the 15th century, ocean-faring explorers such as Columbus and Magellan were extending the reaches of the known world. These voyagers took map makers with them to record the new lands that they discovered, and navigation charts were highly valued. Map makers, who now had a great deal of information about the world to set down, were challenged by the difficulty of representing the curved surface of the Earth on a FL page. One of the earliest attempts to tackle the curvature problem for large-scale maps was made by the Belgian cartographer Gerardus Mercator in the 16th century, and it is still used today. A number of other systems, or map projections, have been developed to translate the curved geographic grid to a FL1. The polar projection is normally centered on either the north or south pole. Meridians are straight lines radiating outward from the pole, and parallels are nested circles centered on the pole. The map is usually cut off to show only one hemisphere so that the equator forms the outer edge of the map. Because the intersections of the parallels with the meridians always form true right angles, this projection shows the true shapes of all small areas. That is, the shape of a small island would always be shown correctly, no matter where it appeared on the map. However, because the scale fraction increases in an outward direction, the island would look larger toward the edge of the map than near the center. In the Mercator projection, the meridians form a rectangular grid of straight vertical lines, while the parallels form straight horizontal lines. The meridians are evenly spaced, but the spacing between parallels increases at higher latitude so that the spacing at 60 degrees is double that at the equator. As the map reaches closer to the poles, the spacing increases so much that the map must be cut off at some arbitrary parallel, such as 80 degrees north. This change of scale enlarges features near the pole. The Mercator projection has several special properties. Mercator's goal was to create a map that sailors could use to determine their course. A straight line drawn anywhere on his map gives you a line of constant compass direction. So a navigator can simply draw a line between any 2 points on the map and measure the bearing or direction angle of the line, with respect to a nearby meridian on the map. Since the meridian is a true north-south line, the angle will give the compass bearing to be followed. Once aimed in that compass direction, a ship or an airplane can be held to the same compass bearing to reach the final point or destination. But this line does not necessarily follow the shortest actual distance between 2 points, which we can easily plot out on a globe. We have to be careful. Mercator's map can falsely make the shortest distance between 2 points appear much longer than the compass line joining them. Because the Mercator projection shows the true compass direction of any straight line on the map, it is used to show many types of straight line features. Among these features are FLO lines of winds and ocean currents, directions of crustal features, such as chains of volcanoes, and lines of equal values, such as lines of equal air temperature or equal air pressure. That's why the Mercator projection is chosen for maps of temperatures, winds, and pressures. Humans long ago decided to divide the solar day into 24 units, called hours, and devised clocks to keep track of hours in groups of 12. Yet, different regions set their clocks differently. When it is 10:03 a.m. in New York, it is 9:03 a.m. in Chicago, 8:03 a.m. in Denver, and 7:03 a.m. in Los Angeles. These times differ by exactly 1 hour. How did this system come about? How does it work? Even in today's advanced age, our global time system is oriented to the sun. Think for a moment about the sun moving across the sky. In the morning, the sun is low on the eastern horizon, and as the day progresses, it rises higher until at solar noon it reaches its highest point in the sky. If you check your watch at that moment, it will read a time somewhere near 12 o'clock, noon. After solar noon, the sun's elevation in the sky decreases. By late afternoon, the sun hangs low in the sky, and at sunset it rests on the western horizon. Imagine for a moment that you are in Chicago. The time is noon, and the sun is at or near its highest point in the sky. You call a friend in New York and ask about the position of the sun. Your friend will say that the sun has already passed solar noon, its highest point, and is beginning its descent down. Meanwhile, a friend in Portland will report that the sun is still working its way up to its highest point. But a friend in Mobile, Alabama, will tell you that the time in Mobile is the same as in Chicago, and that the sun is at about solar noon. How do we explain these different observations? The difference in time makes sense because solar noon can only occur simultaneously in places with the same longitude. Only one meridian can be directly under the sun and experience solar noon at a given moment. Locations on meridians to the east of Chicago, like New York, have passed solar noon, and locations to the west of Chicago, like Portland, have not yet reached solar noon. Since Mobile and Chicago have nearly the same longitude, they experience solar noon at approximately the same time. Standard time simplifies the global timekeeping problem. In the standard time system, the globe is divided into time zones. People within a zone keep time according to a standard meridian that passes through their zone. Since the standard meridians are usually 15 degrees apart, the difference in time between adjacent zones is normally 1 hour. In some geographic regions, however, the difference is only 1/2 hour. The United States and its Caribbean possessions fall within 7 time zones. 6 zones cover Canada. According to our map of the world's time zones, the country spanning the greatest number of time zones is Russia. From east to west, Russia spans 11 zones, but groups them into 8 standard time zones. China covers 5 time zones but runs on a single national time using the standard meridian of Beijing. A few countries, such as India and Iran, keep time using a meridian that is positioned midway between standard meridians, so that their clocks depart from those of their neighbors by 30 or 90 minutes. Some states or provinces within countries also keep time by 7½ degree meridians, such as the Canadian province of Newfoundland and the interior Australian states of South Australia and Northern Territory. Take a world map or globe with 15 degrees meridians. Start at the Greenwich 0 degrees meridian and count along the 15 degrees meridians in an eastward direction. You will find that the 180th meridian is number 12 and that the time at this meridian is, therefore, 12 hours later than Greenwich time. Counting in a similar manner westward from the Greenwich meridian, we find that the 180th meridian is again number 12 but that the time is 12 hours earlier than Greenwich time. We seem to have a paradox. How can the same meridian be both 12 hours ahead of Greenwich time and 12 hours behind it? The answer is that each side of this meridian is experiencing a different day. Imagine that you are on the 180 degrees meridian on June 26th. At the exact instant of midnight, the same 24-hour calendar day covers the entire globe. Stepping east will place you in the very early morning of June 26th, while stepping west will place you very late in the evening of June 26th. You are on the same calendar day on both sides of the meridian but 24 hours apart in time. Doing the same experiment an hour later, at 1 a.m., stepping east you will find that you are in the early morning of June 26th. But if you step west, you will find that midnight of June 26th has passed, and it is now the early morning of June 27th. So on the west side of the 180th meridian, it is also 1 a.m. but it is 1 day later than on the east side. For this reason, the 180th meridian serves as the international dateline. This means that if you travel westward across the dateline, you must advance your calendar by 1 day. If traveling eastward, you set your calendar back by a day. Air travelers on Pacific Sea routes between North America and Asia cross the dateline. For example, flying westward from Los Angeles to Sydney, Australia, you may depart on a Tuesday evening and arrive on a Thursday morning after a flight that lasts only 14 hours. On an eastward flight from Tokyo to San Francisco, you may actually arrive the day before you take off, taking the date change into account. Actually, the international dateline does not follow the 180th meridian exactly. Like many time zone boundaries, it deviates from the meridian for practical reasons. The United States and many other countries observe some form of daylight saving time, in which clocks are set ahead by an hour, sometimes 2, for part of the year. Although it was once thought that adding daylight hours to the end of the workday would save electricity and reduce traffic accidents and crime, the evidence now shows that the primary effects are economic, allowing more retail shopping and recreation, for example. Although something of a mixed blessing, daylight saving time is now a part of normal life in most places. In the United States, daylight saving time comes into effect on the second Sunday in March and is discontinued on the first Sunday of November. Arizona. Except the Navajo Nation, Puerto Rico, Hawaii, U.S. Virgin Islands, Guam, the Northern Mariana Islands, and American Samoa do not observe daylight saving time. Although many other nations observe daylight saving time, they do not always begin and end it on the same days of the year. In the European Union, daylight saving time is called summertime. It begins on the last Sunday in March and ends on the last Sunday in October. Since the 1950s, the most accurate time has been kept using atomic clocks, which are based on the frequency of microwave energy emission from atoms of the element cesium cooled to near absolute zero. These very accurate clocks keep time to better than 1 part in 1 trillion. Atomic time is a universal standard that is not related to the Earth's rotation. Civil time sources use Coordinated Universal Time, UTC, which is derived from atomic time and provides a day of 86,400 seconds. 24 hours, in length to match the Earth's mean rotation rate with respect to the Sun. Coordinated Universal Time is administered by the Bureau International de l'Heure, located near Paris. So far, we have discussed the importance of the Earth's rotation on its axis. But what about the Earth's movement as it orbits the Sun? We refer to this motion as the Earth's revolution around the Sun. The Earth takes 365.242 days to travel around the Sun, almost a quarter of a day longer than the calendar year of 365 days. Every 4 years, this time adds up to nearly 1 extra day, which we account for by inserting a 29th day into February in leap years. Further minor corrections, such as omitting the extra day in century years, are necessary to keep the calendar on track. The Earth's orbit around the Sun is shaped like an ellipse, or oval. This means that the distance between the Earth and Sun varies somewhat through the year. The Earth is nearest to the Sun at perihelion, which occurs on or near January 3rd. It is farthest away from the Sun at aphelion, on or near July 4th. However, the distance between Sun and Earth varies only by about 3% during one revolution because the elliptical orbit is shaped very much like a circle. For most purposes, we can regard the orbit as circular. Which way does the Earth revolve? Imagine yourself in space, looking down on the North Pole. From this viewpoint, the Earth travels counterclockwise around the Sun. This is the same direction as the Earth's rotation. The Moon rotates on its axis and revolves about the Earth in the same direction as the Earth rotates and revolves around the Sun. But the Moon's rate of rotation is synchronized with the Earth's rotation so that one side of the Moon is permanently directed toward the Earth while the opposite side of the Moon remains hidden. It was only in 1959, when a Soviet spacecraft passing the Moon transmitted photos back to Earth, that we caught our first glimpse of the far side. The phases of the Moon are determined by the position of the Moon in its orbit around the Earth, which in turn determines how much of the sunlit Moon is seen from the Earth. It takes about 29.5 days for the Moon to go from one full moon to the next. Depending on where you live in the world, the effects of the changing seasons can be large. But why do we experience seasons on Earth? And why do the hours of daylight change throughout the year, most extremely at the poles, and less so near the equator? Seasons arise because the Earth's axis is not perpendicular to the plane containing the Earth's orbit around the Sun, which is known as the plane of the ecliptic. If we extend the imaginary axis out of the North Pole into space, it always aims toward Polaris, the North Star. The direction of the axis does not change as the Earth revolves around the Sun. Let's investigate this phenomenon in more detail. On December 22nd, the north polar end of the Earth's axis leans at the maximum angle away from the Sun, 23½ degree. This event is called the December solstice, or winter solstice in the northern hemisphere. At this time, the southern hemisphere is tilted toward the Sun and enjoys strong solar heating. 6 months later, on June 21st, the Earth has traveled to the opposite side of its orbit. This is known as the June solstice, or summer solstice in the northern hemisphere. The north polar end of the axis is tilted at 23½ degree toward the Sun, while the south pole and southern hemisphere are tilted away. The equinoxes occur midway between the solstice dates. At an equinox, the Earth's axis is not tilted toward the Sun or away from it. The March equinox, vernal equinox in the northern hemisphere, occurs near March 21st, and the September equinox, autumnal equinox, occurs near September 23rd. The conditions at the two equinoxes are identical as far as the Earth-Sun relationship is concerned. The date of any solstice or equinox in a particular year may vary by a day or so, since the revolution period is not exactly 365 days. The Sun's rays always divide the Earth into two hemispheres, one that is bathed in light and one that is shrouded in darkness. The circle of illumination is the circle that separates the day hemisphere from the night hemisphere. The subsolar point is the single point on the Earth's surface where the Sun is directly overhead at a particular moment. At equinox, the circle of illumination passes through the north and south poles. The Sun's rays graze the surface at both poles, so the surfaces at the poles receive very little solar energy. The subsolar point falls on the equator. Here, the angle between the Sun's rays and the Earth's surface is 90 degrees, so that point receives the full force of solar illumination. At noon at latitudes in between, such as 40 degrees north, the Sun strikes the surface at an angle that is less than 90 degrees. The angle that marks the Sun's elevation above the horizon is known as the noon angle. Simple geometry shows that for equinox conditions, the noon angle is equal to 90 degrees minus the latitude, so that at 40 degrees north, the noon angle is 50 degrees. One important feature of the equinox is that day and night are of equal length everywhere on the globe. You can see this by imagining yourself located at a point on the 40 degrees north parallel. As the world turns, you will be in daylight for exactly half the day and in night for the other half. Now let's examine the solstice conditions. The June solstice is shown on the left. Imagine that you are back at a point on the lat. 40 degrees north parallel. Unlike at equinox, the circle of illumination no longer divides your parallel into equal halves because of the tilt of the northern hemisphere toward the sun. Instead, daylight covers most of the parallel, with a smaller amount passing through twilight and darkness. For you, the day is now considerably longer, about 15 hours, than the night. About 9 hours. Now step onto the equator. You can see that this is the only parallel that is divided exactly into two. On the equator, daylight and nighttime hours will be equal throughout the year. The farther north you go, the more the effect increases. Once you move north of lat. 66 1/2 degree, the day continues unbroken for 24 hours. 66 1/2 degree parallel is positioned entirely within the daylight side of the circle of illumination. This parallel is known as the Arctic Circle. Even though the Earth rotates through a full cycle during a 24-hour period, the area north of the Arctic Circle will remain in continuous daylight. We can also see that the sub-solar point is at a latitude of 23 1/2 degree N. This parallel is known as the Tropic of Cancer. Because the Sun is directly over the Tropic of Cancer at this solstice, solar energy is most intense here. The conditions are reversed at the December solstice. Back at 40 degrees north lat, the night is about 15 hours long, while daylight lasts about 9 hours. All the area south of 66 1/2 degree S lat lies under the sun's rays, inundated with 24 hours of daylight. This parallel is known as the Antarctic Circle. The sub-solar point has shifted to a point on the parallel at 23 1/2 degree S lat, known as the Tropic of Capricorn. We have carefully used the term daylight to describe the period of the day during which the sun is above the horizon. When the sun is not too far below the horizon, the sky is still lit by twilight. At high latitudes during the polar night, twilight can be several hours long and provide enough illumination for many outdoor activities. The solstices and equinoxes are 4 special events that occur only once during the year. Between these times, the latitude of the sub-solar point travels northward and southward in an annual cycle, looping between the tropics of Cancer and Capricorn. We call the latitude of the sub-solar point the Sun's declination, figure 1.24. As the seasonal cycle progresses, the polar regions that are bathed in 24-hour daylight, or shadowed in 24-hour night, shrink and then grow. At other latitudes, the length of daylight changes slightly from one day to the next, except at the equator, where it remains the same. In this way, the Earth experiences the rhythm of the seasons as it continues its revolution around the Sun.